Today we're going to look at two-dimensional vector geometry. So this follows on from the work that you did in the Learning Pack, and it takes us into geometry, by which we mean we'll be looking at diagrams and applying our vectors knowledge to those diagrams. So in this first example, we can see in the diagram the points A and B have positions vectors A and B respectively. This means that they have a vector which has a starting point of O. All right, position vectors always refer to a starting point. We're told then that the point P divides AB in the ratio 1 to 2, and we're asked to find the position vector of P. The first thing I like to do with a diagram like this is to actually write in that ratio 1 to 2. It just keeps me right when I'm going to be doing the work in a bit later on. So if we're interested in the position vector of P, that is the journey from O to P. Now, I recommend you always write out the journeys using capital letters first and then substitute any of the little letters in afterwards. So from O to P, I would describe this journey as being O to A along a vector that we know, plus the journey from A to P, which is a vector that we don't know. Okay. Now another reason for doing this is because it does show you what you need to find. So we know this, OA is little a, AP is something we need to find out. So over here, I'm going to have a look at AP. And one thing that I know about AP is that it's a fraction of AB. So it is 1/3 of AB because of the ratio 1 to 2. Now AB is something that I can write using small letters. So we are able to write the vector AB in terms of small a and small b, because the vector AB is going backwards along OA, so we'll say it's minus OA plus OB, which is exactly what you did when you were drawing the little graphs of vectors earlier. So AB is OB, which is little b, minus OA, which is little a. Now I always put little lines underneath my vectors because I can't write in bold. I suggest you do the same, but you won't be marked down if you don't do it. So we can go back to OP now and say that it's OA, and then it's going to be plus AP, which, as we said, was 1/3 of AB. And then on the next line, I'm just going to write in all of my lowercase letters. So OA is lowercase a, plus 1/3, then open a bracket for this B minus A. And then we just expand and collect like terms. So we have 2/3 A plus 1/3 B. Now that's pretty much a standard GCSE level problem, and I'm hoping that won't cause you too many problems. The second example I have is slightly more interesting, slightly more tricky. We have a parallelogram OABC. Diagonals OB and AC intersect. The vectors A and C are equal to OA and OC respectively. Prove the diagonals bisect each other. So the first thing I'm going to do is actually mark on my vector A and my vector C. Now I can also add in that this CB is also vector A and this AB is also vector C. We may or may not need them, but we know they're the same. It doesn't matter that they don't start in the same position. It is just that they go in the same direction. So prove that the diagonals bisect each other. I'm interested in the diagonals OB and AC. So it makes sense to write down those two diagonals using vectors that we know. So OB is OA plus AB, which is A plus C. Okay, so he's getting used to those vector journeys now. The other diagonal, is AC. And for A to C, I'm going backwards along A and forwards along C. So I'm going minus OA plus OC, which is C minus A. So now I'm interested in this vector OP, all right? And what I'm going to do is I'm going to write that two different ways, one involving diagonal OB and the other involving the diagonal AC. And I'm going to make those two the same, and I'm going to find out that they do bisect each other. So from O to P, I can go about it first of all by saying that it's some fraction. We use the lambda is the constant that we tend to use when we're working with vectors, and it's lambda multiplied by OB. So O to P is some fraction that we don't know of OB. That's what this means. And I can go further and say that is lambda then of A plus C, because I know that OB is A plus C. So I'm going to write OP in a different way that involves the diagonal AC. So I've got OP then is going to be OA first, from O to A, and then plus some fraction of A to C. So I'm going to use mu, which is the second go-to letter that we have typically when working with vectors. And I'm going to say that that's mu of AC. So O to A plus a fraction of this diagonal. So rewrite using my lowercase letters. AC, C minus A. And so now I have two different ways of writing OP. Now one thing that we do know is that OP is a single vector. So we can equate those two. They must be the same because they represent the same line. So the next stage then is about comparing coefficients. We're going to compare the number of A terms on the right-hand side with the number of A terms on the left-hand side. We're going to do the same thing with C. So to do that, I'll multiply out my bracket. So I've got lambda A plus lambda C with A plus mu times C minus mu times A. Since I'm interested in the number of A terms, I've got lambda on the left. How many do I have on the right? Well, I'll rearrange this slightly. Lambda A plus lambda C equals, so A minus mu A is A multiplied by 1 minus mu, just kind of factorizing that A term with this A term, and then plus mu C. Now that tells me two things. It tells me that the number of A's on the left here, lambda, is equal to the number of A's on the right, 1 minus mu. Lambda equals 1 minus mu. By comparing the coefficients of C, I can see that lambda equals mu. So now we're solving a pair of simultaneous equations. And we'll go ahead and just substitute. Okay, so we'll substitute 2 to 1. And we can just say that lambda, therefore, is 1 minus lambda. So therefore, 2 lambda is 1. And so therefore, lambda is 1/2. And if lambda equals mu, then mu equals 1/2. And those halves represent the fraction along the diagonals. OP is now 1/2 of OB. Going back to the diagram, OP is half of OB. And we also know that OP is A plus half of AC, because mu is a half as well. And so we have our complete proof. Now that's a key thing. It's a recurring theme in vectors questions, that of comparing coefficients. Write out all your vectors as clearly as you can, and then compare coefficients later on. And by comparing coefficients, it's literally counting the number of A's on the left with the number of A's on the right, the number of C's on the left with the number of C's on the right. And the final example for today is finding the size of an angle. Okay, I just paused the recording then because someone came in the door, and I hope it didn't lose too much information, but I'm going to start off by looking at the side BC. So to use the cosine rule, we need to know the side BC because we need three sides. In order to find out what BC is, we'll work backwards. So we'll go from B to A. So we've got minus AB plus AC, which is we're already good at and practiced that. We've got AC minus AB. It's like saying the second minus the first. So our AC was I minus 5J, and our AB was 3I minus 2J. And you'll see those little lines that I put under the vectors. So we've got 1 minus 3, which is minus 2I, minus 5 minus minus 2, which is minus 3J. So that means that the magnitude of BC is the square root of minus 2 squared plus minus 3 squared, which is the square root of 13. So we have our third side as the square root of 13. So now that we've got three sides, we're going to use our cosine rule. Now the way that most people remember the cosine rule is as a squared equals b squared plus c squared minus 2bc cos A. That's the way that we normally write it. We're trying to find the angle, so we need to do a bit of rearranging. So we can say 2bc cos A equals b squared plus c squared minus a squared, just adding that to both sides, taking this from both sides. So cos A is b squared plus c squared minus a squared over 2bc. Okay, some of you have got it memorized that way, which is absolutely fine. So now it's just about substituting in. B and C are interchangeable. Okay, so I could call this B, I could call this C, as long as the one opposite is A because you're subtracting it. So what have we got? B squared 13 plus C squared 26 minus A squared, which is 13, divided by 2 multiplied by root 13 multiplied by root 26 2bc. And we'll work all that out. And we've got 26 over 2, just working this out on my calculator, to root 13 root 26. Just got a little error in the calculator there, there we go, which is root 2 root 2. So therefore A is going to be arc cos root 2 over 2. Make sure your calculator's in degrees. And you find that it's a 45 degree angle. So there we have three examples of two-dimensional vector geometry. First one, fairly basic, GCSE level, using a ratio. Second one, a little bit more difficult because we had to prove that this was the bisection of two diagonals, which meant that we had to write the vector OP in two different ways, using each of the diagonals, and then we had to compare our coefficients. I'd say that's one of the trickier parts that you're going to come across, but it is quite a standard process. And then in our final one, cosine rule. Okay, now that's it. Have a go at the questions that I've said.